Welcome back to Differential Equations. In this lecture, we're going to put all of the previous lectures on first order ODEs to use, and we'll be taking a look at application problems for first order ODEs spanning problems from physics, engineering, and mathematics. All right, so to get started, there's a lot of ways we could approach these application problems, but for a differential equations course, not assuming too much background in physics or engineering, one of the standard starting places for us will be from physics with Newton's second law, F equals ma. So even through your basic Calc 1 and Calc 2 courses, you probably haven't encountered enough to understand the relationship between derivatives and instantaneous rates of change. All right, so let's go into detail for this physics application type problem. We're gonna see some examples in a moment, but let's review some terms as well as notation, probably standard from your Calc 1 course. All right, so let's suppose we have a problem dealing with one-dimensional motion. So we're just moving in one horizontal dimension or one vertical dimension, doesn't matter. So we might denote the position as a function of time by x as a function of t. And what you kind of learned towards the middle of your Calc 1 course is, given position, how to find velocity and acceleration. And that's where the idea of derivatives come in as instantaneous rates of change. All right, so with position, we denote that by x of t. Let's denote the velocity by v of t and acceleration by a of t. All right, what we want to do is turn Newton's second law, F equals ma, which looks like an algebraic equation, which it might have been in an algebra-based physics course. We want to turn that into what it actually is, a differential equation. And this is going to come by looking down there at acceleration. We have two different ways to think of acceleration. We could say acceleration is the first derivative of velocity with respect to time, or we can say acceleration is the second derivative of position with respect to time. And if we plug those in, those two different expressions for A in Newton's second law, what we get here are two different types of differential equations. The upper route, where we're replacing the acceleration with the derivative of velocity with respect to time, that gives us a first order ODE, which is what we're going to focus on in this lecture. Later in our course, once we get into second order ODEs, we'll take a look at how to deal with that bottom route, replacing the acceleration with the second derivative of position with respect to time. That'll give us a second order differential equation, that requires more mathematical tools to deal with. So we'll just focus on the first one there, Newton's second law. We're rewriting it as the differential equation F equals m times dv over dt. All right, another standard place for applications problems to arise in a differential equations course is with what are called mixing or flow problems. And these are going to be pretty boring for us, but they're incredibly general and important through a whole host of engineering applications. So the basic problem is there's something flowing, some sort of substance in and out of a tank. For some biological applications, maybe the tank is not like a physical tank, but maybe it's a heart, and what's flowing in and out is blood with different medications dissolved in your bloodstream. We're not going to go that route, but you can generalize it to that. So the basic generalized version we're going to consider is there's a tank, and in that tank there's a substance, and there's something flowing in with the substance and something flowing out. And the question that we would eventually be able to answer by solving a differential equation is, how much of the substance is in the tank at a given time? All right, and as it turns out, that's going to amount to solving a differential equation. We're going to have a different starting place, like the above with physics. We're going to typically start with Newton's second law, F equals ma, but for mixing or flow problems, we're going to start with the concept of net change, or in this case, a net rate of change. So due to the flowing in and flowing out of whatever that substance is, the net rate of change of substance in the tank, which remember you can interpret rates of change, instantaneous rates of change as derivatives, we're going to say that the rate of change of substance in the tank equals the rate at which that substance is flowing in minus the rate at which it's flowing out. All right, and we're going to go into detail with that kind of net change equation, I'll call that there. We'll go into detail that later in a following part of this lecture. All right, now before we go into any actual questions, let's give a overview of how this process works, how we take an actual physical problem and then turn it into mathematics that we can ideally try to solve. All right, so what we're going to focus on right now is a general process of building or creating a mathematical model for a physical system. And this is one of the most important skills that you can kind of learn in a science, engineering, or mathematics course. Yes, even in mathematics, there's a lot of interesting mathematics that come from looking at physics problems. All right, so the basic idea is we have a complicated physical system, and we want to translate that into a mathematical model. So equations, something mathematically that represents that physical system. Now, if you think of your typical physical problem, there are a large number of forces, different effects, different variables that go into that physical system. So if you kind of make your physical system too realistic, it is too mathematically complicated to be able to solve. All right, so let's take a look at how we'll actually simplify this. So the first thing we'd want to do for whatever our physical system is we want to identify the quantities that change or influence the system. Typically in a physics course, like a Physics 1 or Physics 2, the quantities are all the various forces acting on an object. All right, part of the problem with this is if you include too much, in other words, your model is too realistic, maybe due to all the forces, the equations are too difficult to solve. So what you want to do is introduce enough quantities that change or influence the system to get an actual model, but you want to simplify it a little bit to make the equation solvable, I'll say. And this is where, in our mathematical modeling process, you might introduce some simplifying assumptions. And typically in a physics course, you might recall all the problems where you've neglected resistance, neglected air resistance, and projectile motion problems. Those are some simplifying assumptions. One of the examples we'll be getting to, we will not be neglecting air resistance, and we'll see mathematically how that complicates things. All right, so if you have your physical system and you look at the quantities that change the system, and you introduce some simplifying assumptions, your mathematical model ideally represents your system, and it's actually also solvable. Now, the point of making the equation solvable is that you want to be able to go back with your mathematical model or equations and then make predictions about your physical system. And that's typically how theoretical science works. You have a theoretical model. The model, you then use that to make predictions about your system, whatever that is. All right, now this is a good point in our course for me to mention one of my favorite bad math or physics jokes. There's a lot of different variations of this, but here's the version I like. So the joke goes, there's a farmer and he wants to increase the milk production of his cows. So the farmer writes to the nearest university asking for their brightest scientists to write reports on how he can increase the milk production of his cows. So a few weeks go by, and then in the mail he gets reports from a chemist, an engineer, all the brightest minds, and he looks at the report from the physicist. And the farmer reads his report from the physicist, and it says, let's start by assuming we have uniform, spherical, frictionless cows. I told you it was bad. But the punchline, spherical cows, that's our simplifying assumption here. So we have a nice sketch of a spherical cow there. All right, so the whole process here sounds very simple, and you've done some of this in your Calc 1 word problems, if you remember, kind of, I'll say, related rates and optimization problems. That's translating a word or a complicated problem into mathematics. We're going to be building on that here, and as you continue beyond our course, you'll keep coming back to this and maybe add some more details into this. All right, so let's take a look at a kind of a complete example dealing with kind of a physics problem that incorporates this whole process of mathematical modeling. We're going to basically go from our physical system here, basically an object falling due to gravity, and we're going to be including air resistance. We'll get a differential equation. We'll then solve that differential equation, and then we'll use that solution to make a prediction. All right, now all the examples that we'll be looking at within this lecture, they're all going to be first order differential equations, but more importantly, almost all of them are going to be linear. So make sure you are comfortable with linear form of a differential equation. We have it as dy over dx plus p of x times y equals f of x. You want the derivative and the function term on the same side. And we have a formula for how to solve that using the integrating factor in terms of p of x. Now, the examples we'll be looking at here might not be using y as the function and x as the variable, but we can make replacements, which is kind of the beauty and power of mathematics. All right, if you're feeling up to it, pause and give an attempt at this. If you do not feel comfortable with some basic physics, let's just go through part A together. The whole point of part A is to get us to a differential equation, which I would like you to then solve for part B. All right, so the basic problem is there's an object of mass m, and it's falling under the influence of gravity and air resistance. So there's two forces acting on the object, the gravitational force or weight pulling it down, and then air resistance, which is going to kind of slow it down. All right, and we're going to make a simplifying assumption. There are many different types of mathematical formulas for air resistance. We're going to make the assumption that the air resistance is proportional to the object's instantaneous velocity. Now, before we go any further, let's understand why that may be a reasonable assumption. Suppose you are traveling very slow. The force of air resistance on you is then very small. Start running or travel in a car where your speed is a lot greater, then there's going to be a greater force of air resistance acting on you. So small speed or velocity, small air resistance, large speed or velocity, large air resistance. So that's the proportional aspect there. Okay, so let's go through part A. If you have a good background in physics, you might feel comfortable with part A. All right, and our starting place, any time we're dealing with forces, position, velocity, acceleration, we're going to want to go back to Newton's second law, F equals ma. All right, so the notation that we'll use, which is standard for our course, v of t will denote the object's instantaneous velocity, and then dv over dt, the derivative of velocity, that's what we know as acceleration. All right, we're going to replace in Newton's second law the acceleration term a with dv over dt. All right, again, we are not in a physics course, so I'm being sloppy with notation, but the force, F there, that really should be interpreted as net force. And here we have two forces, the gravitational force and air resistance acting on the object. All right. From a basic physics course, you might recall that the weight or gravitational force near Earth's surface is mg. M is the mass of the object, and g is the gravitational acceleration, 9.81 meters per second squared. And the formula for air resistance, we're translating that from our simplifying assumption above. The K that appears there, that's called a proportionality constant. So we'll say the force of air resistance equals a constant times the velocity. All right, so let's try to visualize maybe a simple sketch. In your physics course, this might have been a force diagram, something of that nature. All right, and we have the weight pulling the object down or acting down, and then the air resistance opposing the direction of motion. So that would be acting up in this orientation. Now in physics, you get to choose a coordinate system, and since we're going to be basically releasing the object and it's going to fall down, we're going to decide to call the down direction positive. Opposite that, up, would then be negative. You can do it with your sign switch, but this just makes the differential equation look a little simpler. All right, so all we're going to do from here is just replace the two forces, the gravitational force and then air resistance, into the left side of Newton's second law. mg, the weight or gravitational force, is acting in the positive direction. Air resistance is now acting in the negative direction from what we decided. All right, and what we get here is a first order differential equation for the velocity. Now for our course, I don't expect you to go through this, part A, since there's no official physics prereq for this course. But if you understand this, you're in great shape for some of the more complicated examples that you might be getting to in other courses. All right, when you're ready, we'll advance to part B, which will be solving that differential equation for the velocity. All right, now at this point, I'd like you to make an attempt at this. Even though part A, you might have felt uncomfortable with, maybe if you had no background in physics, you should be okay from our course content in solving this differential equation. All right, now for our class right now, when we go through this example, I'm going to solve it as a separable equation. In a homework assignment, you'll solve it as a linear equation. So right now, try this by solving that differential equation by separating. We'll check in a few minutes. All right, welcome back. Hopefully that went well. If you couldn't solve it by separating, maybe you tried to solve it and were successful solving it as a linear equation. But let's go through and solve this by separating. All right, so first thing I'm going to do is I'm going to divide the whole equation by m. All right, and the factor of m, the mass, cancels out in one spot on the left side, and it cancels out on the right side. Notice also on the left side, we get an m in the denominator of the kV term. All right, we're going to continue to rewrite this to put it in the correct form of a separable equation. I'm going to try to simplify this algebraically to make some of the integrations easier. And what I'm going to do is factor out negative km, or negative k over m, from that left side. All right, if you're uncomfortable with that, just distribute it, negative k over m, into the parentheses, and it should cancel out to what's above on the left side. All right, and then from here, it should be very easy to separate by cross-multiplying, cross-dividing. So you can multiply your dt term over to the left side and then divide the term in parentheses with v to the right side with dv. All right, at this point, it is now separated correctly. The integrations should be pretty straightforward from here. All right, k and m are both constants on the left side. So when you integrate the left side, you'll just get negative k over m, because it's a constant, times t, and then plus c, your integration constant. And on the right side, the integration with respect to v, that's just a simple natural log, but of v minus mg over k. All right, the directions for part B do ask you to get an explicit solution for the velocity. So we're going to want to solve this for v, specifically v as a function of time. So notice where v is inside the logarithm on the right side. You can exponentiate. And then to solve for v explicitly, it's just a matter of adding mg divided by k to the other side. So here we get our explicit solution for the velocity, and we're even given an initial condition. So at time 0, there's an initial velocity, which we're denoting as v sub 0. Now with that initial condition, we can solve for c, and you should find c comes out to v sub 0 minus mg over k. And if you plug that in, we get our explicit solution for the velocity. All right, hopefully you were successful with that. Again, here we solved it as a separable differential equation, but we could have also solved this as a linear equation if we rewrote it appropriately. All right, what I want to do now is complete the mathematical model process. And we're going to take a look at a follow-up. What happens if the object falls for a long time? Now, this is where we're considering the gravitational force as well as air resistance. Now, you might know physically what happens. For instance, if a skydiver jumps out of a plane, after a certain period of time, the skydiver no longer accelerates. That's where the skydiver's weight balances and is equal to the force of air resistance. The skydiver has achieved terminal velocity. Now, let's suppose you didn't know that was going to happen. Let's suppose you were a differential equation student. Maybe you're about to jump out of a plane. Don't do that. And you would want to know what happens if you fall for a long period of time. Now, mathematically, long periods of time, that might be when time, or t, approaches infinity, and that exponential term, that's what we might call a decreasing exponential. I have a very simple graph of y equals e to the negative x there, familiar going all the way back to a pre-calculus course. Here, we're just using a different variable, t instead of x, but as x or t goes to infinity, that decreasing exponential approaches 0. Now, if you take a look at your explicit solution for the velocity above, if that exponential term goes to 0, that means the velocity does not approach 0, only the exponential term becomes 0 or approaches 0, but rather the velocity approaches mg divided by k. And that quantity, mg divided by k, that is terminal velocity. As time goes on towards infinity, the velocity actually approaches a finite number. That's what we interpret physically as terminal velocity. All right, so hopefully you enjoyed this first example. It's a thorough example in the mathematical modeling process, starting with Newton's second law, getting a differential equation, solving that differential equation, which is the goal for our course, and then a follow-up of using your solution to make a prediction. When you're ready, part 2 takes a look at the other typical mathematical model for what we're going to call mixing or flow problems.